So today, as I promised, we are going to talk about the not introduction, but like the basics of probability. So I'm going to talk about the basic concepts today, hopefully, and we will try to start to put together these concepts into something a little bit more complex on Monday in class. So why do we need to learn about probability first? So remember, when we talked about statistics at the first class, we said that we want to learn something about a population. However, it is very, very unlikely that we have the means and the resources to actually study each and every member of the population. So we need to take a sample to study instead. And probability theory provides a basis that we can use for statistical inference. So from our sample, we can conclude some things and we can correlate it or infer some things about the population from the sample. So for example, imagine this questionnaire. So this is just a simple questionnaire in which I ask the respondent's gender. So say here, the results that I obtained are, I got two responses that were female, and 8 responses that were male. So using this information that I just got from my questionnaire, don't forget my questionnaire was conducted on a sample, not a population. If I were to select any respondent at random, what is the probability I select a female? Can you please tell me in the chat box? Then what's the probability that I select a female among all of the respondents I have? 1/5, Dylan said yes, 20% or 0.2, that's correct. But remember, this response, 1/5, 20%, 0.2, that is valid and that reflects the sample only. The sample that I took in this case consists of 10 members or 10 people. So when I say what's the probability of my respondent being female, the response 0.2 is only valid for my sample. But remember, if I take a correct sample, the sample that I'm talking about should be able to represent the population at large. So if I have a big enough sample, or if I repeat this experiment, this questionnaire enough times, I get a big enough sample or a frequent enough sample, so I can use the answer 0.2 or 1/5 to answer about the entire population. And that is why we say that probability can provide us the basis to infer something about our population at large. So here is our menu for this topic. I try to divide into 6 main subtopics that we are going to talk about in order to understand about probability and how we can apply it to our questionnaires or to our data. Today, my target is to go over the first 3, sample space and events, complement, combinations, and algebra, and axioms of probability. Because these 3 things, I believe you probably already know about. So the first is about the sample space and events. So the sample space is what we have when we do an experiment. What's an experiment? So an experiment is anything or any process, any activity, any procedure for which more than one outcome is possible. So multiple things could happen and we don't know what will happen. So that is an experiment. So if you remember in our very first class, I remember someone said, when I asked, what does statistics remind you of? Someone said dice, right? So that is one experiment. Throwing a dice is an experiment because we have 6 possible outcomes and I do not know what will happen. So I don't know which outcome will come up. So the sample space is the set of all possible outcomes. So what could happen? Anything that could happen from this experiment, from this dice toss, then that is my sample space. So for example, if I toss a coin, my sample space is heads and tails. If if my experiments is running a race among the six horses, then the possible outcomes are all orderings of 1, 2, 3, 4, 5, 6. So like all possible outcomes of the race results of these 6 horses. And the last one is if I want to determine the correct dosage to give medicine to a patient, then this is probably my sample space. So either 1 dosage, 2 dosages, and 2 doses, 2 dosages, and so on. So as you noticed from my example, we talked about dice, right? So these are games of chance that are often used for an illustration of probability cases, like tossing a coin, rolling dice, and the use of a pack of cards. So it is easy to imagine because of a roll of a die, we have 6 sides and we have a sample space of 1, 2, 3, 4, 5, and 6. And if we have 2 dice, then our sample space is a tuple or a combination of 2 results. So here we have 36 possible outcomes for 2 dice. But now we have the sample space, which is all possible outcomes. Since I mentioned previously that these are what could happen, right? And I don't know what will actually happen. So when something in fact happens, we can say that an event occurs. So if the sample space previously was the set of all possible outcomes, the event E is a subset of S, any subset of S. And if the outcome of the experiment is contained in E, we can also say that E has occurred. So for example, when we talk about the event in which an even score is recorded on the roll of a die, my event is 2, 4, 6. Heads if I toss a coin, and the event that number 3 horse wins the race. So previously we had orderings of 1 to 6, right? There are 6 horses. So E is all of the outcomes in S starting with a 3. So number 3 horse is the first result. So here we have the concept of sample space and events. You might have noticed that when we were writing down S and E, we used our squiggly brackets. What are these brackets in English? Like these kurung kurawals. The name escaped me at the moment. But my point is this is the correct notation of a set, right? You remember set theory. You already learned this previously, I believe, in discrete math. So please note that I will require you to write using the correct notation when you are depicting and when you are indicating outcomes of an event or sample spaces, because these are all sets. Speaking of sets, it's not only a simple set that occurs or is our sample space, right? When we talk about events, when we talk about experiments, it's not always that straightforward in the sense there's only 1 dice or there's only 1 horse or whatever. But usually when we consider events in real life, we have a combination of different sample spaces, combinations of different events, which will result in a combination of different sets. So this is one question that came up in your quiz just now. So which terminology is used in set theory? Hopefully you still remember this set theory, which is the complement, which is the union, which is the intersection, and which are the subsets. So since I believe you should already know this from your previous classes, I'm just going to skip over to a drawing that I made. So recall, when I'm talking about the sample space, I'm talking about my universe, right? I'm talking about all possible things that could happen. And when I talk a certain event, the event here is a subset of the sample space. When I say complement or EC, E complement, I'm talking about everything else except E. So here, the yellow, no, sorry, not yellow, the orange line shows the complement. So everything that's shaded in orange here. So everything in the sample space except. Next, we have the union, E and F, or E union F. So here, this is the black line that I use to indicate E union F, which is E and F. We also have the intersection, E intersection F, which is indicated here with yellow, which is this sliver between E and F. So it's the overlapping areas or overlapping elements of E and F. Lastly, we have subset and proper subset. So here I made an example of a subset, which is G here, which is a subset of E. In this case, we can say that G is a proper subset of E because it is smaller than E. However, I could also say that E is a subset of E. And in this case, this is not a proper subset because they are also equal. So if you would like to review the concepts, the following slides give you the definitions of complement, union, intersection, and subset and proper subset. Oops, sorry, the animation is late. So in this case, for example, AB is a proper, is a subset of ABC and a proper subset of ABC. However, when I'm talking about the same set, I can say that ABC is a subset of ABC. However, it is not a proper subset of ABC. And of course, as a consequence of these complements combinations, we also have the algebra of events. We have the commutative law, distributive law, associative law, and De Morgan laws. I will not be going into detail on this because I believe it should already be covered in your discrete mathematics course. I'm going to take a pause here. Okay, so now we have our events, right? We have all of the possible things that could happen. We also have the subset, which are the events that actually happen. So now I want to compute the probability of these said events. Apologies, did I continue recording? Yes, I did. Okay. So the concept of probability, like as I mentioned previously, if I do an experiment, in the example I showed previously, it was a questionnaire. If I do an experiment enough times, I repeat it again and again under the same exact same conditions. So for any event E, the proportion of times that E occurs will approach some constant value. So in my previous example, when I was taking a questionnaire and asking the gender of my respondents, if I do that enough times, the probability of the proportion of times the response is female will will converge to a certain value eventually. And this proportion, that fraction is called the probability of event E. So in my previous example, it is this proportion of females, which is my event E, event in which my respondent is female. Or we can also read it as how likely will the event E occur. In the previous example, how likely is a respondent to be female? We also write this using the mathematical notation P in brackets E. Don't forget, if you are answering a question in your exam or in an exercise, you need to define what E is first before you can define its probability. Like, so for example, in our previous example of probability, I can say that if the event E is the event, okay, apologies beforehand, I forgot to connect my digital pen, so I'm using my mouse here. The event that the respondent is female, and the probability in our previous example was 0.2, 20%, or as Dylan said, 1. Be careful to always define what E you're talking about, and then you can define its probability. Note that you do not have to use the word E, right? I hope you know that. You do not have to use the word E, the letter E, you can use whatever letter you like. Okay, so after we know what the concept of probability is, now we have some rules, some axioms that we can live by when we compute probability. So I'm going to take you back to some of these quizzes. Okay. So here I said that I know that the probability that it will rain today is 0.8. How large is the probability that it will not rain? Most of you, actually all of you, answered 0.2. Would anyone please tell me how you got 0.2? You can use the chat box. Resume. So for the next question, we have the probability of event E, PE, equals 2. This statement, also, you guys, most of you answered, this statement is incorrect. This is also correlated to the answer in my chat box that says the max probability is 1. Correct. It's not possible for us to have a probability larger than 1. Remember, what was the definition of probability? It was a proportion. It was a fraction. So it will definitely be under 1. So this one was a little trickier. If the probability of E is 0.5 and the probability of F is 0.5, then the probability of E or F must be 1. So E or F is the union, right? E union F must be 1. You guys were not wrong to add up 0.5 and 0.5. However, you must have forgotten the E intersection F. What happens if E has an intersection with F? It will not equal to 1. We'll look at this in the next axis. And finally, if the intersection of event A and event B is an empty set, they both can be described as mutually exclusive. So if it's an empty set, the intersection is empty, then they are not intersecting each other, or in other words, they are mutually exclusive. And in this case, if we know that the events are mutually exclusive, then yes, the sum of their probabilities must be equal to 1. However, in this question, we do not know yet if they are mutually exclusive or not. So that brings us to our axioms of probability. So we have 3 axioms as a basis. So for each event E of an experiment that has a sample space S, there is a probability, which was a proportion, remember, where this proportion will follow 3 axioms. 1, the value of the axiom, the value of the probability will always be between 0 and 1. Note that it can be equal to 0 and can be equal to 1, but the value will be definitely between 0 and 1. Axiom 2, if we have a sample space, the probability of the entire sample space will equal to 1. Remember, what is our sample space? Oops. Here, that's our sample space. Everything will be equal to 1. The probability of everything will be equal to 1. And axiom 3, for any sequence of mutually exclusive events, E1, E2, E3, and so on, the sum of them, sum of their probabilities will equal the probability of the union. So this axiom 3 and axiom 1 will follow will give us two consequences. First, if proposition 1 says that the probability of the sample space equals to 1, that means the probability of E union E complement, remember? So this is one event and this is everything else that could happen, will be equal to the probability of itself and its complement. And as such, the complement will be 1 minus PE, which you guys already answered correctly just now in the quiz and in the chat box. And lastly, following the axiom 3, recall when we said that the sum of the probabilities will equal to the probability of the union. That was valid for mutually exclusive events only. If the events are not known to be mutually exclusive, or in general, the probability of the union will be the sum of each probability. So in this case, E union F, PE plus PF minus PE intersection F. In the case of mutually exclusive events, this is an empty set. And as such, the probability is 0. So we do not need to do this subtraction, and we can just sum them up simply, just like in axiom 3. But that is only valid when they are mutually exclusive. If they are not mutually exclusive, we need to subtract their intersection. And this is just the last consequence. There are 2 more slides here on axioms. So when we have a sample space that consists of events O1 until On, then the probability of each O, each possible outcome, must be between 0 and 1. We already learned that in axiom 1. And the sum of all of the events will be equal to 1. And following that, since we're talking about sets, then we have some properties of probability. So as we already mentioned, when we have an empty set, the probability of that empty set is obviously 0. Complements, 1 minus the union is as such. And if we have subsets, then we know that the probability must be less than the outer set. Is that the correct term? I'm not so sure. Okay, I'm going to take another pause here. Are there any questions? Okay, so now we have an example. The probability that a student passes math is 2/3. The probability that he or she passes biology is 4/9. The probability that he or she passes both courses is 1/4. So the question is, how large is the probability that he or she passes at least one course? Remember when I talked about the correct notations for sets, I said that you have to always define your letters, your events, before you can compute your probabilities. So in this case, I defined 2 events: M, the event that the student passes math; B, the event that the student passes biology. And now, what do we know about these 2 events? The probability that M occurs, or the probability that the student passes math, is 2/3. The probability of B occurring is 4/9. And the probability that he passes at both courses, so P, M intersection B, which can also be written as PMB, will be equal to 1/4. So since we know that these 2 events, now we have both here, so we know that they are not mutually exclusive. So if I would like to compute the union of both, what's the probability that he or she passes at least one course? So either M or B. PM, oops, sorry, plus PB minus the intersection. I believe so. And, oh, it has already been computed. So we have, this is the computation. I have one more example that I'm not going to do in class, and I'm going to leave you to do it on your own. The answer is available on your on the slides that I published on schedule. Okay, so up until now, we have computed the proportion slash the fraction slash the probability of certain events happening. So up until now, we had this assumption. Implicitly, we already assumed that the sample spaces, every element of the sample space has an equally likely outcome. So here, if I ask you, if a dice is rolled, what is the probability that its face will equal 6? So what's the probability that if you roll a die, you get a 6? You guys agree if I say 1/6? Would you agree? You can use the chat box. Would you believe me if I told you that I'm rolling a die and I want to compute the probability that I get a 6? Is it correct for me to say the probability is 1/6? Would you believe me if I said that? Matthew believes me. Does anyone else believe me? Okay. So I'm going to ask you, are you sure? Are you actually sure that it's 1/6? Why are you sure? What assumptions are you using to answer 1/6? If we're going to be really, really technical about it, actually, it's not always 1/6. But we must have this fundamental assumption in place. If we assume that all possible outcomes are equally likely to occur, then yes, 1/6 is the correct answer. Why do we need to conduct this? Because if I'm assuming a fair dice, this is going to be the result. But what if my dice is a little wonky and like there's a weight to it? Actually, the probability is not 1/6. And as you all know, life is not fair. So sometimes it doesn't work that way. However, for every computation that we will conduct in this statistical and probability class, we will use the assumption that sample spaces have equally likely outcomes. This is a crucial assumption that is the basis of all of our probability computation. So if I use that assumption, I can then formulate the 1/6, the 1/6 that we talked about yesterday. Not yesterday, the previous slide. How did I get 1/6? I was talking about a die, right? So when I have a die, I know that I will have 6 possible outcomes. And I know that 6 is one possible outcome. In other words, if I follow the axioms of probability, I now can define the probability of any event happening by actually counting the number of members. So I can define the probability as the proportion of number of members in E over number of members in S, in sample space, or large N. So this is the basis of us computing any type of event probability. I just count how many times, how many members occur in the event and how many possible members were there. So if I use the assumption of rolling a fair dice, then I can compute that the point of even is, I'm just counting 1, 2, 3, the numbers of members in the event, in E, the number of members in E over the number of possible members. So 3/6. And in this case, for 2 dice, then I need to compute, oh, how many elements here? How many members do I have in my event? 1, 2, 3, for 5 members. So it'll be 5 over all possible members, 36, right? 5 over 36. And we can apply the same logic for any combination. So if I have A, B in this case, and I would like to compute both dice have even scores, so I just need to compute how many how many members do I have in my E. So if my E is both have even scores, so it's this one, that one, that one, that one, that one, that one, this one, that one, and this one. I have 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 over a total of 36. And it's as simple as that. I need to count how many do I have in my event, how many do I have in total. So it seems quite easy. Oh, then I just need to compute how many members do I have in E, how many members do I have in total. However, if you have a question, a soal cerita, it is not always that easy to deduce how many combinations do I have in the nominator? No, the denominator and nominator. Is that the correct word? Please correct me if I'm wrong. So how many combinations I have on the top or how many combinations I have on the bottom. For example, if a family has 3 children, find the probability that 2 of the 3 children are girls. If we assume that all outcomes are considered equally likely, then I can write my sample space as follows. It could be a boy, 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 girl, girl, and so on. There are 8 possible outcomes. If we assume that each outcome is equal, then each has a probability of 1 over 8. And the question asks, what's the event that 2 out of 3 are girls? So my event consists of 1, 2, 3 probabilities, 3 members, sorry. So I could just compute, okay, that's just 3 over 8, right? But in this case, I had a family of 3 children. So it wasn't very difficult for me to actually write out all possible combinations of children, right? For boy, 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 girl, and so on. And here, the event that we found 2 out of 3 are girls. It wasn't very difficult for me to actually write them out. But what if I'm not talking about children, but I'm talking about students at UI? I'm no longer talking about 3 positions or 3 people. I'm talking about 4,000 people. It's not that easy for me to actually write out all possible combinations of 4,000 people, right? Boy, 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 until 4,000. Boy, 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 until 3,999. Girl. It's not realistic for me to actually write out all of these possibilities. Thankfully, we have rules of computing combinations. We have the product rule, we have permutation, we have combination, we have circular permutation, and we have ring permutation. So I believe that all 5 of these concepts, you probably have already encountered them before. And this is where I'm going to end the lecture for today. So I urge you to look at these 5 different ways in which we can compute the combination of events. We're going to start our lecture on Monday from here.